Hi everyone, I'm Julia,
Hi, I'm Paula.
and together we are responsible for the development of Serenity Star. We are also active users of Azure Database for PostgreSQL. We've been using it for the past couple of years as part of the infrastructure setup of our platform, and we want to share with you some of the lessons that we've learned along the way.
Today we'll walk you through how we implemented Retrieval-Augmented Generation in Serenity Star, including some of the architectural decisions behind it. We will talk about the challenges we face and how we solve them using Azure for Database for PostgreSQL.
Okay, everyone, let's just get right into production RAG at scale with Azure Database for PostgreSQL. Just a bit more about ourselves. I'm the VP of product of the platform, and Pau joining me today is the architect of Serenity Star. And what we do actually is that we work with implementing AI at an enterprise level. What we have right now is a platform that's called Serenity Star, used for managing AI agents. It is a live product with thousands of agents and millions of executions, and we use Azure Database for PostgreSQL for our RAG implementation. The idea of this session is to walk you a bit through Serenity Star and what an AI agent means and is for us. We will showcase the RAG agent pipeline and walk you through some of the architecture decisions and structure that our platform has. We will then analyze the performance issues that we had over the last years and how we worked to solve them, and also what are the different monitoring tools that we have available, again, thanks to Azure Database for PostgreSQL. So what is Serenity Star? Again, it is a platform where all of the different aspects required for having a productive agent are considered. It considers security, compliance, costs. We can analyze usage, have monitoring of that, even fine-tune a model if required. And of course, we have RAG for our agents. We have a combination of multiple LLMs and connectors that allow for any task to be resolved. We offer, from our side, a SaaS deployment where multiple tenants can work and can coexist. But we also offer the possibility of having a deployment on any cloud based on what our clients require. Again, there is where Postgres is a great ally because it works on any of the different clouds that we want to work with. I've been talking about AI agents, and I think it's important to give a definition of what we consider an AI agent to be. On our minds, they have 4 different dimensions: cognition, behavior, capabilities, and knowledge. When we talk about cognition, we talk about the AI model in itself, and it's the LLM that ends up executing that AI request. When we talk about prompt engineering, we talk about defining the behavior that that agent is going to have to perform. And of course, in natural language. That's the whole idea of this LLM working with us and for us. When we talk about capabilities, there's a whole layer of orchestration and integration that comes into place. We can orchestrate multiple agents or integrate with external APIs or external databases and make our agents work along with that. And lastly, when we talk about knowledge, we talk about Retrieval-Augmented Generation, or RAG. That is the process that allows us to give the LLM contextual information that is relevant based on what the user is requesting. Throughout this talk, we will walk you through our knowledge pipeline. There are a lot of different ways of doing RAG, but we will show you the implementation that we have for this. We will now show you a demo to illustrate this knowledge pipeline to contextualize all of the technical specifications that we will be seeing later on. We are looking here at the SaaS deployment of Serenity Star using a specific tenant created for today. I will access the AI agents index from the sidebar, where we can see that we have an AI agent defined that for this example is an expert in PostgreSQL, specializing in Azure Database for PostgreSQL. When we access this specific agent, we can now see the Agent Design Studio, where here on the left, we see the possibility to configure all of the dimensions that we were just discussing. We have the behavior, the model, the skills, and I will particularly access the knowledge section by clicking on its card. On the left side, we now see the list of all of the knowledge sources that were already added. a card for each. Website links with relevant information were used for this example, but we could add as many as needed. I will add a new source to illustrate this process, specifically a Word document that was prepared for this, that has a lot of relevant information on the SQL language. When we add this file, the content of which will be extracted, chunked, and embedded using a specific model chosen by the final user and then stored in our Postgres database. We now see that the file is available to use. It's as quick as that. And when we access here from the card the sections of this file, we can see all of the chunks that were generated. If needed, each of these chunks could be even modified directly from our platform to avoid having to reprocess everything. When we make any change to our agent, such as adding a new source in this case, we are generating a new version, as can be seen from this badge on the top. We now have pending changes. This is a very important feature for us because we work with then productive implementations of the agents. And as Paula will explain later, this also causes a lot of challenges when it comes to storage volume as we maintain backwards compatibility for all of these versions. If I save these changes, and now we will try to execute our agent, we will now work with all of these different chunks that were created for each of the files. If I, for example, ask this question, how do I set up zone redundant high availability in Azure Database for PostgreSQL, we will now obtain the response from an LLM. What is important from this step is that we first executed this searching relevant knowledge task, that is our RAG task, and so we are sure that the agent is answering based on that information. We will wait for the agent to finish its response. And now what is also very interesting for us is that when we access the detail of this conversation, we can see all of the knowledge sources that were found as relevant. I will zoom out just a bit. But from here, we can see for each of the chunks of each of the different sections, which were selected and what was the relevance of each of these chunks. If we need to dig in a little further on the visibility of this and the traceability of this, we can access that section in particular, the same one that we were seeing from the designer, and see all of the detail context that was added. And so just to summarize what we were just seeing, when we upload a new knowledge source, that knowledge file goes through 4 different stages. First, the scanning step, where we extract all of the content from that knowledge source that we are receiving. Then the chunking step, that's where we transform that large context into small chunks that we can work with. Then the embedding step, when we work with transforming that text into a vector using, of course, an embedding model. And lastly, the storage step, where we store all of those vectors and some relevant information that Paula will talk us a bit more about into our Postgres database. These vectors are stored until they are needed and retrieved for the agent's execution. When we talk about the agent's execution pipeline, this is the more complex part of our platform, but this is a simplified graphic of that. We first generate that agent execution context that contains all of the definition for that agent, and of course, the specific version that we may be executing, as we were seeing on the demo. Then on the knowledge module, based on all of that configuration, we transform that request of the user into a vector, again, using that same embedding model. And we do the similarity search with some specific queries that Pau will be showing us later on. And lastly, with all of the results from that query, what we do is that we make the official AI request to the chosen LLM and, of course, the corresponding API that we need based on that. I will now leave you with Paula, who will walk you through some of the technical aspects of the implementation.
Okay, thank you, Julia. Hi, everyone. Okay, let's take a quick high-level look at our architecture. We have at the top our clients and our users that interact with the application through our various web interfaces. We have also some independent services at the top right. We have a scraper service and an asset manager service that help us to process websites and contents of files and turn that into knowledge. We all of this is hosted in Azure. We have some application services, Docker containers, database services, and more all running on Azure. And the application itself is a .NET 10 application. So if we take a look at the logic of the applications, zooming in a little bit, we will see that the logic is basically evenly split between agent management and agent execution. The agent management is what we were seeing earlier with Julia of how you can add knowledge to your agent and add tools to your agent and configure it so it behaves the way you want it to. And the agent execution, it's what happens in the agent execution pipeline. The Julia also introduced it just now, where the user sends a request for the agent to complete. And this request turns into a virtual agent, basically that gets filled with context and tools and all the things that it needs to be run and complete the request, including some models and providers that you can see on the right. Um, and all of this is supported by Microsoft Agent Framework, which allows us to hook in our agents with different models and different providers. And when I say model, I'm not only talking about embedding models, I'm also talking about LLM models and even image generation models and audio generation models. And finally, if the solution, of course, is supported by various databases. On the left, we have the model and audit databases where we have our agent data and our logs, basically. We have a cache database in Redis. And more importantly, we have a Postgres database in Azure Database for PostgreSQL. And this is where we start our knowledge. And this was actually one of the earliest architectural decisions that we made. We decided to separate the knowledge information into a different database using Postgres because we wanted to keep the workloads regarding the RAG workloads separated so it doesn't impact other operations in the system and it doesn't get impacted by other operations. So now that we have this context, we can focus on the main issues that we face early on and through this whole process of developing this system. So first of all, one of the first issues that we find was supporting multiple embedding models. And the main issue here is that different embedding models support different vector sizes, so you can't just store every embedding generated by every model in the same column, in the same table, in the same database. So that means you need to somehow decide which column to use for each embedding model. So, for example, OpenAI's text embedding small, 3 small, has an embedding size, a vector size of 1,536, while the Gemini model has an embedding size of 3,072. So we need to use different data types for that. The way that we solved that, it was actually a pretty simple solution. We decided to have a different table for each embedding model that we wanted to support. So each table has their own different name, obviously, and it can have the embedding column set with the data type that we need to support the vector size that we need for each embedding model. And eventually, we also ended up adding the vector size to the table name because we realized that some embedding models also support different vector sizes, like the same embedding model has different vector sizes. So that's basically our simple solution to this particular issue. Then the other thing is basically growth, how our database grows, how our tables grow. Um, so Serenity Star is a multi-tenant application. So that means we have multiple tenants, multiple users, and everyone can create agents, and agents can have multiple files, and files are separated in multiple chunks. And on top of that, we support versioning. So people can edit files and change the embedding model, and that means we need to reprocess the embeddings for that particular file or for those particular chunks. So that means the data keeps growing and keeps reproducing because we don't want the user to have to reprocess the files and generate the embeddings again every time they switch back and forth from one version to another. We want them to be able to do some A/B testing or something like that. So That means we have to keep storing every version in the database continuously, and we are currently over 1.4 million records in our database. Um, and actually, Azure Database for Postgres was a great choice for this because it allows us to scale as we grow. And this obviously takes us into performance and optimization. Um, because the bigger the tables get, the slower they can become. So we will take a look at the similarity search query for starters. Here we have your typical similarity search query using cosine similarity to retrieve the 5 more relevant records in the entire table. So this type of query is okay and good enough if you have like a single agent or a couple of agents that share the same knowledge sources. So for us, this is not enough, basically. We need something a little bit different. In our case, we are still applying the cosine similarity operation that we saw earlier and taking the 5 more relevant records, or the n more relevant records, actually. But we also included a few filters that allow us to make sure that the agent gets the context that's relevant for that particular version of the agent in that particular moment. So this is necessary for us to have like an accurate context, but does not guarantee that the query will be fast enough for our purposes. In fact, once this table started to grow after a few months after we deploy all of the first solution, we started to notice some delays. We started to notice some queries that were taking around 1 second, 2 seconds, and even a few timeouts when we have like high concurrency in our systems. So what we did is basically a pretty, I think, the next step for us was to create a multi-column index. This index basically covers the main filters that we were seeing earlier in our um, all of our queries, basically. So it was a pretty effective solution to improving performance in across the whole system, because we are always filtering by tenant, by agent, and by version for sure. So we went from queries that took like a few seconds to queries that took around 70 milliseconds or so. It was a really a game changer for us, actually. We will see more about timing and how this improved later in the monitoring section with Julia. So, I don't want to just say that the query just improve and not tell you a little bit more about it. So we are going to take a look at the query plans. This is the query plan. I mean, what happened with our query when we didn't have any indexes. So this explains what was happening before. So if we take a look at the bottom right, we can see that there are some stages. One of them is called sequential scan, and then we have the gather stage, and those two are actually pretty heavy. We can see that the cost is pretty high, and that it took like half a minute, half a second, sorry, to solve those particular stages, and that only retrieve 47 rows actually. But it was a pretty costly operation, and then we apply the sorted and the limit that we see on top. But after we apply our indexes, here's the query plan that we got. We're still getting these same 47 rows, but it's taking quite a lot less. It's taking like a fraction of a millisecond. This is obviously cached, so obviously sometimes it takes a little bit more, sometimes a little bit less, but it was a pretty obvious improvement for us, and the cost is obviously a lot lower. So the index scan operation that goes directly to those records that are filtered by agent, by tenant, and by file version, that really made a huge change for us. If you're interested in exploring your queries and getting these query plans and seeing what you can improve and how you can work on improving the performance of your queries, I highly recommend you take a look at this extension by Microsoft. This extension gives you these pretty cool diagrams that we were seeing earlier for the query plans, and it also integrates your Postgres database with Copilot, so it can provide you some insights on why the query plan is doing what it's doing and how you can improve it and what you can do with it, basically. So really cool. I highly recommend you take a look at it. And before we move on to monitoring, I wanted to share a little bit about the DiskANN index. This is something we are exploring. It's not in production yet, but we find it really, really interesting, and we wanted to share a little bit about it. The DiskANN index is an approximate nearest neighbor index that works on your vector columns. So it optimizes operations such as the similarity, cosine similarity operation we were seeing earlier. So it's really useful when you have like a huge data set with a ton of vectors that you have to sort through using the embedding column. And it's directly integrated in Azure, so you can enable it pretty easily from directly from your Azure portal, and then you can simply create the index and start testing it out. The documentation is really good. You can find a lot of performance tips in there, and how obviously how to enable it, how to create the index, and all of that, the obvious things. But there's also a ton of really cool information in there. For example, we found it really, really useful. There was a table that explained which parameters you can set for your index depending on your dataset size. That was really cool to have. So I highly recommend you take a look at that. And that was all from me. We can move on to monitoring with Julia.
Thank you, Pau. Going back, as we were mentioning from the beginning, we really think that this is an interesting case since we are really productive, and it's been some interesting couple of years working on this and on all of the different aspects. And as Paula was mentioning, it was an architectural decision for us to choose Postgres, and then also a strategic decision to use Azure Database for PostgreSQL and not to try to do this locally. And so we wanted to share what are the actual benefits that we found after these years of doing this. The first one is that it is true. The effortless scalability is a true affirmation when it comes to this implementation. We can, and we actually did increase our computing or our storage settings based on the growth and the usage that our platform was having. We even modified our high availability configuration or our backup setup as our platform and as our productive implementation was growing. And of course, all of this translates directly into cost efficiency. Also, when it comes to resource monitoring, we found it really, really useful and really clear. This is an example of our dashboard where we can always see our CPU and memory usage and how that evolves over time, the database availability, that of course we always want to have it in one, but issues sometimes happen. Then the storage and where we are at on our storage usage, the DB connections or the throughput that our database is having. We always have that information live, and we can also see the history of all of those parameters over time. Again, we went through issues with all of these different aspects during the implementation, and it was always useful to have that information. Also, as it is a live platform used by third parties, a peak usage in one of those third parties can result in an infrastructure issue from our side, almost pretty quick, I must say. And so we also have a whole set of alerts defined that help us understand when any of these anomalies is occurring. And to accompany what Paula was mentioning before about query monitoring and the performance issues that we worked with and that were improved, we also have in Azure Database for PostgreSQL the possibility to see statistics of our queries. The one that we personally use the most is the dashboard for long-running queries, where we can see first an overall average of how much our queries are taking. We can dive into any of the queries if we want and get the exact script that is being executed. And just to show the impact of that index that Paula was mentioning, here we are seeing, well, actually, this is the after, where we have approximately an average of 50 milliseconds over time. We let the platform run with the index for 24 hours to get this image. And this image is of the before. where we let our platform run for 24 hours without the index, and our averages were of about 750 milliseconds or something about around there. We are always looking at all of these metrics and always looking at our query information. It clearly depends on the volume that we have and the usage that we have. And so we are always on top of this to know if it improves or gets worse throughout time. This is all from us today. We hope that you found it interesting and that there are some tips that you can take with you in defining your productive implementations. If there are any questions, please don't hesitate to contact us via email or to the Posette Discord channel. Thank you.
Thanks, everybody.